Hello, my name is Tom C. Tutor, and the little problem we want to look at today is the body on the slope problem. Right, so the original real life problem is to do with a bus on a slope. So there's a slope and there's our little bus. Little bus on the slope here, okay? Now, if this slope was not a slope, as it was a level road surface, then let's look at that first before we start worrying about what happens on inclines. So that's a good way to attack the problem. So if I have my little bus sitting on the road like that, and there's my little bus. Now, because it's on the level like that, and the engine's switched off, and there's nothing happening, the bus is stationary, what forces are acting on this bus? Well, we have the weight of the bus that's acting down, and that's mg. We're told that the bus has got a mass of 4,250 kilograms. Therefore, its weight is just going to be 4,250 times the gravity, which is 9.8. Okay? So on my little calculator, I work that out. And that's wrong. Right, just give me a sec. That's 4,250 times 9.8, and that's got a total weight of 416. I'm going to make it three significant figures, okay? So it's 41,700 newtons, or 41.7 kilonewtons. So that's the weight of the bus sitting in the road there. That. So it's 41.7 kilonewtons. So now I can get rid of all that. So that's the force that's pulling the bus towards the centre of the earth. Now, according to Newton's third law, N3 says that if a body is stationary, there's an equal and opposite reaction. And that equal and opposite reaction there is what we call the normal force, Fn, in this particular case. So Fn must equal that 41.7 kilonewtons as well, but be in the opposite direction. And that's it. That's that problem solved. There's no other forces in the body. There's nothing. You might ask, is there friction? Who cares? It's stationary. It's not moving. There's no forces. It's not as if you're trying to pull it, because if you were there trying to pull a bus in a rope or something, Arnold Schwarzenegger style, pull a bus. If there was no friction, you could pull a bus quite easily. A child could pull a bus. Obviously, okay, I assume we take the handbrakes off. But if there is friction, then he's going to have a problem, because he's going to have to overcome the friction to pull a bus, even to just move it. But we're sort of going away from the original problem, which is to do with the bus on the incline. So that's that problem solved, that bit. So 41.7 kilonewtons. If I may just put that here, mg, it's 41.7 kilonewton. And we'll get rid of all this. Sorry, I'll rewrite that. 41.7 kilonewtons. There you go. Right, now we come to the real problem. The bus is sitting on an incline surface, okay? And we represent the problem with what's called a free body diagram. In the free body diagram, the body that we're talking about, the object, is just a block. It's just a square like that. The fact that it's got wheels and an engine and windows is totally irrelevant, okay? From a mechanical point of view, it may as well be a big hunk of concrete sitting in the road, okay? So it's just a big block. The weight of the bus is acting straight down here, okay, towards the centre of Earth, and that hasn't changed. The weight is still 41.7 kilonewton mg. We have what's called a positive angle of inclination, and we assume that's, that's constant throughout the slope. It doesn't vary. And the bus is not slipping. Now that's important. Handbrakes on the bus, it should not slip. The engine's off. If it is slipping, we don't use this analysis. We use kinetic friction. But if it's not slipping, it's stationary. It's what we call static equilibrium. The body is in a state of static equilibrium. Static means stationary. It's not moving. So the coefficient we're using is a static coefficient. And what we're going to actually work out is, given this situation, how much of an inclination, what's the maximum angle of inclination we can have before the bus does actually slip. And that's called the point of slip. The point of slip is the maximum angle that the slope can have. And that's the question. That's what we have to work out. Okay, looking at the free body diagram, I set up a coordinate axis. I've got x going plus x going up the hill, 90 degrees of that. I've got plus y perpendicular to that, so that's what we call normal to the plane. That's at 90 degrees to the plane there. That's my y. Okay, 90 degrees. Now, you can have your axis orientated any way you like. I'm choosing this particular orientation. That is x that way and not that way. X that way. Because it makes the calculations easier, that's why. Anyway, what do we know? We know it's in a state of static equilibrium. Therefore, the sum of all the forces in the body, called the resultant force, which is big F, is the vector addition of all these forces in this body. That must be equal to 0. Okay, and that requirement is Newton's second law. Because it is zero acceleration. If it's zero acceleration, the unbalanced force, which is the resultant force on the body, must be 0. If it's static, stationary, it can't have any acceleration. Okay, so let's work out the resultant. Let's vectorially add up all these forces, vectors, and we have to sum them so that they're 0. If the force is 0, then its components must also be 0. And that's an important thing. So, the sum of all the x components of this resultant force, okay, what is that? What is that? Well, it's the sum of all these forces up the hill. Well, I'm assuming that the force, what called the resistance force, sometimes called the reaction force. Okay, but best not to use that, just stick to friction. The friction force up the hill, I'm assuming it's going up the hill. How do I know it's going up the hill, not down the hill? Because the friction, I'll put it here, Fr, the friction force opposes the direction of motion. That has to be because of conservation of energy. Because if it was in the same direction as the motion, there would be a force propelling the object and giving us free energy from nothing. And that doesn't happen. So that force has to be up the hill, because the natural tendency of the motion for this bus is down the hill. Obviously, the bus slides down the hill. So that's these are two comments that are very important to analysing this problem, and it's something you should make a statement of that fact, because you don't just slap in these equations and try and solve them. You have to make certain assumptions, and this is the assumptions we're making. So the f of x here is my f of r up the hill minus a component of the weight that's acting down the hill. And the component of the weight acting down the hill is w sine theta. Because this is a little triangle, and that's theta, and that's w there. The hypotenuse is w. Therefore, this component, the opposite component, is w sine theta. It's negative because it's in the negative x direction. Okay. Now we have one other little formula that helps us here. Is that friction force is proportional to this force called the normal force. So let's write this whole thing as, but let's just take it out and just put mu f n in there, like that. Okay, there you go. And the only thing I have at the moment is that and that. So I've actually got two on mu is 0.4. So I've actually got two unknowns here, f of n and sine theta. I've only got one equation. However, the sum of the fy's in the y direction, these components are the normal force, f of n, going up the hill, take away the component of the weight that's acting down the hill. Now it's not the full weight now as it was in the horizontal case, it's less, it's the component, and I hope you can see that w cosine theta, because that's the adjacent to that angle, so it's a cosine theta. So we have two equations, and two equations, two unknowns. Maybe we could solve that. We can't, because we don't have what these are. So I've actually got three unknowns. Actually, I actually got four. the Fn and sine theta. But remember, we've got these conditions that result in 0. So I have the sum f of x for static is equal to the sum f of y is equal to 0. These components of the resultant force given by f of x and sum of f of x and sum of f of y, they're all 0 because it's a static situation. So that's like the third equation. Okay, so I've actually got three equations here. 1, 2, and 3 equations. And now I can solve it because the left hand side of these is both zeros. I've got two equations and two unknowns. Right, let you ponder and think about that while I clear the boards, get some space. So, to conclude, so far, we have made the assumption that the bus is sitting on what we call a rough surface. Now, a rough surface doesn't mean jog, 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 the traditional sense. It's opposite to a smooth surface. If this was a smooth surface, there would be no friction. Okay, so that f of r would be 0. And the bus would always slip down the hill if it was smooth. So think about a smooth surface in terms of our bus problem as maybe being an icy surface. The bus will slide down the ice, okay? Well, maybe not in reality, but I wouldn't stand in front of it, put it that way. But a rough surface is not a smooth surface because a rough surface has friction. Okay, so there's no such thing really as a smooth surface. Every surface is a friction. We'll talk more about this friction maybe later on, but at the moment we're only interested in solving this particular situation. So let's simplify that. So I'll rewrite all these and I'll just put them as 0. There you go. 0, 0. So I'm using equation 3, okay, and I'm eliminating all that. So now reduced to these two equations. So what do we know here? Let me think a second. Well, it depends what you want to work out. And I want to work out what the maximum angle is I can put the slope to before it slides. So let's work out that first. So from equation 1, okay, we can see that mu Fn is equal to W sine theta. And from equation 2, we can see that Fn is equal to W cosine theta. Okay, so I'm just rewriting the two equations like that. I hope you can see that if I divide equation that by that, I'm going to get mu, in fact I'll just do that, mu Fn over f of n is W sine theta over W cosine theta, and that is equal to tan theta, okay, because the W's cancel, in fact the Fn's cancel as well. Now this is an interesting little equation because that gives what we call actually the critical angle. It is the maximum angle, it's called the critical angle. So the theta critical, let's call it critical, what it is. The theta critical for this problem is the arc tan of mu. And since mu is equal to 0.4 given in the problem, then that is 21.8 degrees, which I've written up above. So that's the maximum angle that the bus is safe to sit on in the road, in theory anyway. And it all depends intimately on this coefficient of friction. Now let's talk about this friction for a moment. The friction has two. The friction depends. The friction force itself depends on the weight because it's mu Fn, remember, and Fn depends on the weight. So it depends on the mass of the bus what the friction force is. But in this problem, that's balanced out by the weight itself. So the weight is cancelled out. This angle does not depend on the mass of the bus. It doesn't matter how heavy the bus is. That angle is fixed, and that's important. So we don't have to worry about, we're going to design more roads to have a maximum angle. We don't have to worry about whether or not how heavy the bus is. It's irrelevant. So we can design a road. It doesn't, just from this. The only thing that determines this angle is that coefficient of friction between the bus wheels and the road. So that angle there, that angle, the critical angle, theta critical, just depends on the material of the road surface and its condition. The condition of the road surface, how literally rough it is, and the material, the rubber that the wheels are made of. That's the only two things that determine that angle for our design. Now, rubber is rubber. Doesn't matter what. The tyres are all made of rubber. in fact, the road is a road. It's asphalt or whatever type of material it is. It's used in your local geolocation. Now let's think about this. What would happen if I had a greater coefficient of static, mu static? Dry conditions versus wet conditions. This mu is it's the worst case scenario. That's the worst case because that's low. Now, how does that work out? Well, that's the wet. So we've designed a road here to have an angle of 21.8 when the road is wet. If it was dry, that would be away up to about 0.7, and that angle would be greater. So for using dry road conditions, your road could be probably about 45, 50 degrees or something. And you say, oh, that's great, I can have a really steep incline, put my buses on it, they won't slide down. But then it rains, and the buses slide down. So you can't do that. We have to use the lowest value of mu. Okay? So if it's dry, the bus will sit there. If it's wet, the bus will sit there. You might have a problem if it's icy, because that will go even lower, and the bus will start to slip. So you have to think about that as well. So we maybe put in what's called in the world of mechanical engineering factor of safety. And I would suggest a factor of safety here of probably 2 at best. So I would not use 0.4. I would design my roads with a mu of, in reality, I would use a design mu of static friction of 0.2. Okay, now I don't know what the arctan of that, well, let's see what it is. So I need the arctan, shift tan of 0.2. That would be 11 degrees, 11.3 degrees. So really, in reality, I would recommend to the designers of the roads that they have a maximum inclination of 11.3 degrees and no greater. That would include a factor of safety, a safety factor if you like, might call it that. A safety factor of ×2 in my design. And the bus would probably not slip even if it was icy. Now if it was, they done tests and they found that the buses were sliding, they could easily just roughen up the surface a little bit, change the material, maybe make it, I mean they can't go mad, you can't have a road like that. You can't design a road surface like that, really rough. Because when you're driving along it, you'd be wasting a lot of energy overcoming kinetic friction. And the energy you would waste would be the force times the distance. And the force, maybe I'll go over that in just a quick second. But you'd be wasting a lot of energy if the surface was really rough. So you can't make it too rough. You have to be efficient in your transport system. So I'll leave the roughness to the road to a separate video. That's kinetic friction, and that's a sort of separate analysis. So that's where inclination problem solved. So hopefully you understand that, and now watch the short video about energy, work, and kinetic friction. Thank you.